Now, complex numbers, when you first see them, they seem very strange, right? The idea is that the real numbers, the ones that we've been working with all up until now, they lie on a number line, all right? So we have the real number line. We have 0, and we have numbers, integers 1, 2, 3, -1, -2, etc. We have all these. We have the integers and the numbers in between. We have rational numbers in here. We have irrational numbers like the square root of 2. We have other irrational numbers like pi. All these things are on this real number line. Well, it turns out that you can expand off of the real number line and view even more numbers. And they live in the other direction. You can think of them as being orthogonal to the real number line, perpendicular. And instead of calling it 1, 2, 3, you call it I. So instead of the number 1 being the basic, 1 is probably the most basic number you can think of as far as the real numbers goes. It's got some nice properties and things like that. Well, I is the basic number in this direction. So you have I, you have 2I, you have 3I, and going the other direction, you have -I, -2I, -3I. And now we have, instead of just a real number line, that's this guy, we have a whole plane of numbers, because we can position ourselves anywhere out here. I could take a point over here, and you can see that in the real number direction I have 1, but in the I direction I have 3I. So this is the number 1 plus 3I. So just by adding these, I position myself somewhere in this coordinate system. If I take a point over here, that's the number 2 minus I, because I went 2 in the real number direction and then down 1 in the I direction. Or I could do, here's -2 plus I. I could do -2 minus 3I. So we have this whole bigger plane of numbers instead of that live off of the real number line. And this is called the complex plane. A two-dimensional flat sheet is just a plane. It extends infinitely in all directions. And so that's what this is called, the complex plane. And so you have the real numbers in the complex plane. Anything on this real number line is in the complex plane, and it's a real number, but you also have things that are off of that number line, and there's other things. And then when you develop this, you can start thinking about, well, how does multiplication work? Well, however multiplication works, it should preserve the way multiplication works for the real numbers. So it shouldn't change that. So is there a way to get multiplication to work the same way on the real numbers, but also work in a meaningful way for the numbers that live out here? And it's kind of surprising, but it's kind of neat how it works. When you multiply two numbers, you look at their angle from the positive real axis. And when you multiply numbers, you just add the angles and you multiply their magnitudes, right? So for instance, if I take the number I over, if I just take, the number I, right there on the complex line. This has an angle of 90 degrees from the real number line. So if I multiply it by 1, I'm going to add the angles. Now 1 is on the real number line, so it has angle 0 off the real number line. It's on it. So its angle is 0 plus 90 is still 90. So 1 times I is still going to be angle 90, so it's still going to be here. And I multiply their magnitudes. Well, they're both 1 unit away from the center. So their magnitudes are 1. You multiply 1 times 1, you get 1. So I times 1 is just still I, right? In fact, anything times 1 is still going to be that number. What if I take I times I? If I take I times I, I'm going to add their angles. Right? So I'm going to take 90 plus 90. So now I'm at 180, which puts me over here. So I times I puts me on the negative part of the real number line. And their magnitudes are 1. So 1 times 1 is 1. So it's the negative number whose magnitude is 1. That's this number right here. It's negative 1. So when you multiply complex numbers, you add the angles, and you multiply the magnitudes, and that's how the multiplication works. You can. I'm not going to do it for these right now, but like you could multiply this complex number and this complex number, and what you're going to do is going to add these two angles together, and you're going to get a new complex number somewhere else, and you're going to multiply the magnitudes, and you'll see how far out it is. All right. I don't want to go too far into this because this isn't a geometry class, but that is how it works. But what we just saw is that when you multiply I times I, you get negative 1. Right? So a consequence of this is that I times I is negative 1. But that means that I squared is negative 1. So what we have is we have a new number that isn't a real number, it's somewhere else, but it satisfies this interesting property that its square is negative 1. Now, when we were only thinking about the real number line, the equation x squared equals negative 1 has no solutions on the real number line. But now we see that it does if we look at complex numbers. This equation actually has a solution. So I is a solution to this. So if we allow complex numbers, we're able to solve equations that we couldn't solve before. Whereas before we would say there is no solution, now we can say that there definitely is. And this whole thing about rotating, it is consistent with how we did real numbers too, because what's the angle for negative 2? Well, it's 180 degrees from the positive real line. So if you multiply negative 2 times negative 2, you're going to add 180 to 180, and you end up back on the positive part. So it makes sense the way negative numbers multiply. Negative times a negative gives you a positive. And it's kind of a neat way to explain why the product of two negatives is a positive. Because we just add the angle, and 180 plus 180 gives you 360. You end up back on the positive part. But this is really all we need for this section, is just to know this fact right here, that I squared is this new kind of number whose square is negative 1. All right. So what we can do with that now is we can use this to write down things that we used to say were just, not a real number or not defined. We used to say does not exist. Well, now we can talk about them. So we can express things in terms of I. So for instance, if I have square root of negative 9, we used to say does not exist, or not a real number would have been a better thing to say. What we can do now is we can say, well, this is the square root of 9 times negative 1, right? And I know that I can always break apart a radical when I have a product. So I can write this as root 9 times root negative 1. Well, square root of 9 is 3. And what's the square root of negative 1? Well, I is that number that when squared gives you negative 1. So we say the square root of negative 1 is I. Right? So this guy becomes I. So that's another way to write down the square root of negative 9. it's just 3i. And by the way, when you take the square root, you're taking the angle in half. And so that makes sense on this picture. If you take a negative number, which has angle 180 from the positive real line, and cut it in half, now you have 90. So it makes sense that it lies on this line. Right? So if you take a negative number and take its square root, you end up with a number over here. Squaring doubles the angle, square roots take the angle in half. So it's kind of neat how that all works out very geometrically like that. What about this one? Square root of -5. Well, you do the same thing, right? You're going to write this as 5 times -1 under the square root. That's the square root of 5 times the square root of -1. The only thing here is that we can't simplify root 5. It's not a perfect square. So we just leave it. Root 5i. Make sure you don't extend the radical over the I. And I like to put a little nook on my radical whenever it looks like it may be confusing. Like if I can't tell, is it over the I or not? Well, I like to put a little vertical part onto it so you can clearly see that it's not, right? That I came out of the radical. It represents this whole thing, root -1. So there should be no root over the I. I kind of contains the square root as part of it. All right. What about square root of -18? Okay, well, here we can write this as 18 times -1. So that's the square root of 18 times the square root of -1. So that's root 18 times I. But you know what, I can do more here because I can simplify root 18. So we should always simplify our answers. So how would I simplify root 18? Well, I'd factor out a perfect square, right? And it has a perfect square in it. 18 is 9 times 2, right? So this is the square root of 9 times 2 times I. And so that's the square root of 9 times root 2 times I. So 3 root 2i would be the simplification of root -18. Let's do some more simplification problems. Simplify. Let's do root -8 plus root -32. Okay, well, root -8, I don't know if you noticed, but whenever we have a negative number, the negative just comes out as an I, right? That's what happened here. Root -18 became root 18i. Root -5 became root 5i, right? Root -9 became root 9i. Oh, so what I was saying is that if you have a negative in here, it comes out as an I, right? So I can just, after making that observation, I think we can see that this is just root 8i plus root 32i. We can kind of skip those steps we were doing before now that we've made that observation. And I can simplify these, right? Root 8 is root 4 times 2. And 32 is, what's the perfect square factor of 32? 16. Right. Okay, so the square root of 4 is 2. So this is 2 root 2i. I'm shaking my, here, let me move this a little. Okay, that should shake less. Square root of 16 is 4, so this is 4 root 2i. Okay, now you can treat I like a variable, right? If there was any letter here, that would make these like terms, right? So I have 2 root 2 plus 4 root 2, that's 6 root 2. So my final answer would be 6 root 2i. Or you could have thought of root 2i as the variable. Like this is the same as this, so I can combine them by adding their coefficients. So that is how we would simplify something like that. So let's do one more where we have i's to begin with. 2 plus 7i plus 4 minus 2i. Okay. Well, what we're going to do is combine like terms. Okay, so let's get rid of the parentheses. 2 plus 7i plus 4, and then plus a minus is just a minus. So I get this. What are the like terms? Well, we have two real numbers here, 2 and 4, so they combine to give me 6. And then I have two numbers on the imaginary line, right? So these are like terms, so I can combine them. 7i minus 2i, 7 minus 2 is 5. So I get 6 plus 5i. So just treat I like it's an x in this case. You do the exact same thing if that was a variable x. We can also multiply these. You multiply this just like you were multiplying two polynomials. All right, so you take 5 times negative 1. That's negative 5. You take 5 times 2i. That's 10i. Take negative 3i times negative 1. Well, negative 3 times negative 1 is positive 3. I. Right? Don't forget the I is there. And then negative 3i times 2i. All right? Well, negative 3 times 2 is negative 6. Okay? Now, what do I do with the I times I? Well, that's I squared. So just like if it was a variable, if this was an x instead of an I, this would be exactly what you get, but with x's here. But we know something special about I squared, right? If you remember, I squared is negative 1. All right, so we can replace it with negative 1. So that's what we're going to do. The negative 5 here, I got 10i plus 3i. Those are like terms, so they combine. That's 13i. And then I have minus 6, and this I squared, negative 1. Okay. So let's see, negative 5 plus 13i. Minus 6 times negative 1 is plus 6. Negative 5 plus 6 is 1. So I get 1 plus 13i. And when we write complex numbers, we always write them in the form a plus bi. All right? So this is the final answer. A plus bi. Right? So the real part comes first, and then they often call this the imaginary part. The thing that's multiplied by I comes next. And every complex number can be written like this. And so don't write 13i plus 1, write 1 plus 13i. That's just the standard way to do it. Okay? But treat it like a variable. You know, if you just treated this like an x and did this, it's exactly the same, except that we have this additional fact that I squared is negative 1. So you'll have no I squareds in the final answer. Okay? And let's do a multiplication problem where we have something like this. Root negative 36 times root negative 4. Okay? How would we simplify this? Well, we said that whenever we have a negative, it just comes out of the square root as an I. So this is just 36i. That's what that guy is. And root negative 4 is, oh, sorry, I forgot the square root, right? Square root of 36i. And then this is the square root of 4i, right? The negative just comes out of the square root as an I. We saw that from the very first examples we did. Square root of 36 is 6. Square root of 4 is 2. And now we multiply. 6, you don't have to worry about like terms when you multiply. That's only for adding and subtracting. So we just multiply everything. So 6, well, we could do the coefficients separately. 6 times 2 is 12. I times I is I squared. You can group them when you multiply. So I'm going to do the coefficients first and then the i's second. Okay. But what's I squared? I squared is negative 1. So what we get here is negative 12. All right, so if you want to solve this for x, there's a couple things you can do. You can multiply this all out, set the polynomial equal to 0, and then try to factor it like that, or use the quadratic formula. But there's another approach to this where you just get the square. Just like we were isolating the square root, you can isolate the square. And that's why I was thinking it was like those other problems, because it kind of is in that sense. You can solve this by getting the square by itself. So what I would do here is add the 3 to both sides. All right, so x minus 7 squared equals negative 16. Okay, so if something squared equals a number, what does this have to equal? You might be tempted to just take the square root of both sides, but you have to be a little careful here. Let's take a little aside. If I had the equation x squared equals 4, right? Just taking square roots of both sides is going to give me one answer. It'll give me x equals 2. But there's actually more than one answer to this, right? There are 2 numbers that when squared give me 4, right? There's 2, that's one of them, but there's also negative 2. Right, so x equals 2, but also x equals negative 2. There's actually 2 answers. And that'll happen whenever the power is even. If it's odd, it doesn't happen. And it has to do with the fact that even powers, the graphs look like this. And so if you pick a number, there are 2 values that correspond. If I take a value, there are 2 different numbers. If this was 4, there's 2 and negative 2. This is a graph of y equals x squared. But the odd powers don't do this. Their graphs look a little bit different, so they don't have this problem. But okay, so that's what we have to think about in this problem up here. Where were we? X minus 7 squared equals negative 16. So if I have something squared equals a number, that means that that thing that I was squaring, in this case x minus 7, is going to equal plus or minus the square root of that number. Okay, that's exactly what we did up here. If x squared equals 4, x equals plus or minus the square root of 4. So same thing. Okay, so let's simplify this thing. Well, we know that the negative comes out as an I. So this is the same as plus or minus root 16i. But I know what root 16 is. It's 4. So this is plus or minus 4i. So there's 2 different answers. So if I add 7 to both sides, what do I get? I get x equals 7 plus or minus 4i. Another way to write this would be, x equals 7 minus 4i. That's one of the answers. Or x equals 7 plus 4i. That means the same thing. And so there are two different ways of writing it. This means or, plus or minus. So you could put it with a minus, write or, and then put it with the plus. So we're really getting two different answers here.